I can't hear anything. I don't know if you can hear me, but can you hear me now? Everybody, can people hear me? Okay, I can hear you. I can hear you now. So we're good. Yeah, more or less, yeah. Okay. Hi, everybody. I can't see any faces, so it's just gonna be me talking to these quiet screens. But I am a PhD student in applied math at UNC in North Carolina. And so yeah, I learned about Julia on an internship. My mentor forced me to do machine learning in Julia instead of learning PyTorch or TensorFlow or something like that. And I love Julia now. And I'm going to share some slides, give you an introduction about it. And then I'm going to show you a few code examples I have. And yeah, basically, I just want to show you why I think it's so cool. So we'll see how good of a job I do at that. And let's start off with this. This is a couple slides I made last year. So let's go to slideshow mode. Actually, we're gonna do it that nice presenter view thing. Okay, here we go. All right. So Julia was designed to solve the two language problem that many of us who program have experienced. So what the two language problem is when you're solving something in programming, you have a language one that's dynamic, but it's slow. It's easy. It's a high level language. It's easy to read, easy to debug, quick to develop and works right out of the box. And an example of this is Python. And if you're an engineer, maybe Matlab. And so what you do is you have your problem that you're working on and you write up your solution in Python, but you can't scale it because Python is too slow. And so when you actually want something for production, you might translate that into C++. And this is my background, I'm more of in research. It's like this is the domain of research scientists where I'm coming from in my background. And so the problem you face in typical software development might be different. But this is a problem I'm very familiar with. And so then you have language 2, which is like C++ or C, Fortran maybe, optimized, fast, low level, but it is hard to read and difficult to debug, and it requires a lot more development time and a lot of language specific expertise. So Julia is trying to be both of those things. It's trying to be language 1 and language 2 at the same time. So here's some benchmark results. Julia doesn't always perform this well for every task, and there are tasks where it's a little more slow and some places where people complain, but this is like incredible. Even if it's not always true, the fact that they were able to do this. So if you look at the language, C was able, a optimized C solution to this problem, some kind of sum. I think it was an integral, an approximation to an integral. I'm not sure. Anyway, this is the C solution, 71 milliseconds. Generic Julia was 72 milliseconds. And so it was faster than C++. And if you look, this is the code that they ran. And I think the C code and the C++ code is, I think, like 4 times as many lines of code, maybe just 2 times. But the fact is, this is a lot easier to read. You're like, absolute value of a sum is greater than absolute value of X. Then you add, plus equals sum. And it just looks like pseudocode, essentially. So that's one of the reasons Julia is cool. You can write code that looks almost like Python, but it can run as fast as C. So Julia is a new language, and there's not enough packages. There's a lot of functionality missing. There's not a lot of great learning resources like there are for Python, and documentation can be scant. So for the project that I was working on, I had to implement a random projection tree library from scratch. Whereas, if you were doing something in Python, there's like annoy, there's a ton of random projection trees or just approximate nearest neighbor search algorithms. They're all there, right? So this is one of the cons of Julia. It's new. And so while it can be fast, you may have to write a lot more code than you would have to in Python. And I'm hoping that it will grow. And I guess time will tell. So anyway, I implemented this random projection trees, which I will talk about later. But before I do that, I'm going to, so we'll just stay on this page for a second. But so pros of Julia, fast and easy to iterate in, like Python. But the cons of Julia are there's a lack of support, and beyond just packages being available, it's kind of like, you're doing a project at your company, and to start up something in Julia, it's like there's just like nobody who does it, right? Like everyone's gonna have to learn Julia, which isn't so hard, but there is a learning curve, right? And so it's kind of like, because nobody does it, it's hard to like start doing a project in Julia. And so it depends on your needs, but my opinion about this is Julia is the best language that I know of for research. So like academic research is what I'm thinking, because I'm a PhD student. But the reason is because when you're doing a research problem that's computational, you don't have to like work with a bunch of other developers, and you're pretty much by yourself and maybe one other person. And in that situation, having code that's this easy to iterate in and that's this fast, right? Because I'll run a lot of stuff on compute nodes, and Julia will just blow Python out of the water and save me a ton of time, getting my project together. So that's a place where Julia is good right now. And it's not like Julia is just a framework for scientific computing, but it's a general purpose language, just like Python. So there's web development in Julia. There's all kinds of different tools, and they're being created, but they don't always exist yet. So if you want to get excited about something and contribute to a cool open source project, Julia is a place where you could do it, and you could be the package that everybody uses, 5 years from now. I mean, if you write a good package. But anyway, so I'm gonna jump into a little more details about Julia. So I've written some Medium articles about Julia 2 years ago, and recently I had a PhD in computer science come and like read through my articles and tell me all the places I got it wrong. And I still have to kind of correct some of them for that. But just to give you an idea, like I know what I'm talking about, but not like really know. Like I'm not a computer scientist. So take what I'm saying with a grain of salt. But I am giving you, even though they had a lot of critiques from me, I feel like I got like the gist of things correctly. But I'm just saying like this isn't like precisely correct, everything I'm going to tell you. So, I do want to read you this quote and give you a little history of Julia. So it says, we want the speed of C with the dynamism of Ruby. We want a language that's homoiconic with true macros like Lisp, with obvious familiar mathematical notation like Matlab. We want something as usable for general programming as Python, as easy for statistics as R, as natural for string processing as Perl, as powerful for linear algebra as Matlab, as good at gluing together problems as the shell. Something that is dirt simple to learn, yet keeps the most serious hackers happy. So huge goals for Julia, but it kind of feels like they did it. There's like, I've been introduced to so many new programming concepts coming into Julia that are so natural, like macros like Lisp, metaprogramming to give good metaprogramming functionality, which is just so cool. And honestly, when I read this statement, I don't know like what homoiconic means. I don't really know what true macros are, right? But I've learned a little bit about it from the Julia standpoint. And so Julia was developed at MIT, I think primarily by a professor named Alan Edelman and his PhD students. And they were all like, they like thought through every detail of the language really carefully to try and create something that just feels the way you think programming should feel. And it has its sharp edges too. But for me, it's just like the mechanisms of the Julia language end up being so beautiful that I long for them when I have to, do program in other languages. So Julia is not object oriented. Everything is a type. And types are, you can do user defined types. Let's see, what do I want to talk about here? And user defined types are pretty much just data classes. And so you never have any internal functions, right? Like if you're going to write a class, you have all of your member functions that are inside of your class. In Julia, they made this decision to divorce functions from objects. So you just have data that's stored in types and functions outside of it. And you'll see a little bit of the reasoning behind this. Functions exist independent of types and objects. And the reason behind this is multiple dispatch, which is similar to overloading, but it's a little bit different. And so I'm just going to talk you through this example to kind of explain how multiple dispatch works. So let's say we need a function f that's going to square its input and compute its value mod 4. And so I'm just going to show you, like, this is what Julia function definitions look like. I guess I kind of jumped into this example too early, but just so you know, so you can define it different ways. This is just different ways of defining f, our function. And okay, we're going to assume that we always need f to output an integer, but its input x can be a string, float 64, or int 64, and we won't know the type of x until runtime. So if you're going to write this in Python, you're going to need to operate differently on a string and differently on a float. But if you get an int, you're fine. You can just run this code. So right, like if type of x is a string, we're going to turn it into a float. If type of x is a float, we're going to take the ceiling of it, and then we're going to return square it and mod by 4. So in Julia, you could do that. You could write this same thing. It's a little more verbose than Python. If is a x string, parse x into a float 64. If is a this, but in Julia, you would be better off writing these 3 functions. And what this is saying is f. This is the version of f that's called on ints, and it just looks like square it mod by 4. This is the version of x that's called on floats. And what you do, so you see something weird. I'm calling f again. It's kind of like recursion. It looks like recursion, but it's not recursion. It's dispatch. So this is where you take the ceiling of your int 64, ceiling of x, and you return an int 64, and then you call f. And what's really happening is, and I'll give you a sec. I'm going to read this last one too. So this is if you get a string, you parse the string into a float 64, and then you call f. And so what happens is f exists outside of your data, and when you pass a variable to f, the compiler is going to determine which version of f to call, and that's the dispatching that happens. And so here, I pass f a string, and the compiler says, okay, we're going to call this version of f. And when this returns a float 64, okay, now we're calling the float 64 version of f. And when this returns an int, then now we're going to call the int version of f over here. And so that's going to give you your final result. And so it does the same thing. And if I was to just pass a float, it wouldn't call this string f. It would just call float f, and that's going to call the int f after. And so this is doing that if statement with, I just wrote it using dispatch. And so dispatch is one of the reasons why you divorce functions from classes, is because you can define your function with the same name to operate on any number of different things. And I think I have a good example of this. I don't think we need to go through any more of this over here. So this is multiple dispatch. I have an example I like. So like this one. So in Julia, sort is something that you do all the time, right? And in here, you're going to create, in Julia, you would create 3 different sort functions that are each going to work on different kinds of input. So this is a sort function for strings, sort function for arrays, sort function for bool. And you can do this with the plot function, for instance. So you can design your own type inside of your project that you're working on, and then you can define what you want the plot function to do for that type that you made. And so then when somebody loads your package and they call plot on one of your types that you created, it's going to generate the kind of plot that you told the plot function to do. And so this, like, it streamlines a lot of different things. So for instance, nested if statements, this is the last example we just went through. Another cool thing is Julia can use this to get rid of redundancy. And so basically, I'm just going to jump through this really quickly, but the compiler will look at your dispatched tree of all the different things that are possible, and it will get rid of the extra code. And I don't know if I should step through this if anybody's going to be interested in this, but basically the compiler will go and optimize. And when Julia gets compiled down to LLVM code, the compiler will remove all the extra pieces that you didn't need, because it will determine, depending on the types, what functions might be called and which ones might not. And see, this is one of the things where the PhD in computer scientists will step in and be like, Anyway, so the other nice thing about this is when you're thinking about development. And this is the piece that I wish for all the time. So let's imagine that a developer wants to count the number of lines of code in a file. In Python, you might write something like this. So open the file, read the lines, close the stream, return the number of lines. In Julia, you can write code that looks about the same. And they are about similar in speed for a lot of files. And I think I could have optimized this better, but I don't know. So anyway, now let's assume that the developer who's writing this uses this function in multiple different places inside of their package. But later it becomes clear that they need the function to operate on different kinds of input as well. So they want to count lines on a single file, a list of files, have capacity to filter files by extension. And this is the kind of thing I feel like I run into all the time, where I wrote a function and now I'm like, okay, well, I'm using this, but I actually, I wish it could also operate on arrays, or whatever, like different kinds of input. And so before we assumed that the count lines function is used in several places. So it'll be helpful if when the function is redefined, it acts exactly the same way it used to act. So it's still going to work in all those places where it used to be. But it also gains new functionality for other inputs. So that way the developer can avoid having to rewrite old code or get bugs in code that was working before. And so it's possible for me to like, define new functions with new names, or to rework the old code by changing names. But if it's a large and complicated code base, switching function names could be bad, especially if the code's collaborative. And if you don't want to change function names in your code, like you don't want to go back and change functions, the Python solution is usually to use args and kwargs. And I'll be honest, you could have a much more elegant solution to this than what I wrote. But basically, in Python, if I use this, star args, the splatter or whatever, now count lines can accept any number of arguments, and I'm gonna make a decision about what I'm gonna do depending on the number of arguments that I get. And then I'm gonna have this little file lines function that essentially was doing before, but now this is doing all the deciding it's doing like the dispatching part. And so you might, this is like a prettier version that someone else came up with in the comments of this article. And so in Julia, like you might be anticipating, extending functionality is much easier. So here's my original count lines function that I defined for Julia earlier. And if I want it to work on an array of strings, I just write count lines of all the files, and I do sum map, and I apply count lines to my array now of files, the original count lines function. And if I want it to work on an array of files and filter by extension, I filter them, and I call count lines again on the filtered array of files, and it's going to call this one, which is going to call this one, right? And so the point is, this is like a way of breaking up the process of extending functionality of some function that you want to do in a very elegant and pretty way. And it's really natural in development. And you can, and because we did not modify this original function, any code that was using this function before is going to be fine. Like nothing changed in your code base. You just need to write tests for the new function. You don't have to like, I don't know, like go back and test all your old code. And okay, so I think that's all I wanted to say here. So we're going to talk. So I've been writing Julia for a couple years, and I'm a decent Julia programmer. I'm not amazing, but I did this project for one of my final projects in one of my classes, and I made a Julia package to do random projection trees. Random projection trees are a generalization of KD trees. It's just a data structure to help you find the nearest neighbors of a high dimensional data point. And so it's something like, it's an algorithm, artificial or approximate nearest neighbors is something that like Netflix uses, Spotify uses to when they have their giant arrays of user data, they want to find users who are close to you in that high dimensional space. And random projection trees work by slicing up data in random ways and kind of like organizing by buckets. I don't really need to go into the algorithm here, but this is my Julia package. And it took me about 4 months, so like the entire time in the class to write it. And it was a pretty concerted effort. And I did my work, but I'm just like an average programmer. And so what happened is my algorithm, so here's this in blue, queries per second is on this axis, and recall accuracy is here because you're approximating. So if you go slower, if you have less queries per second, you can be more accurate. But so up and to the right is the best in this plot. That means that you're more accurate and you have more queries per second that you're doing to find approximate nearest neighbors. And so Shrike, that's me in blue. And I'm faster than Annoy, which is the standard like package that people use for this. And Annoy is a Python wrapper of, I think, C++ code. And MRPT, this is some optimized C++ code. And this is purple is a Julia package, but it's not really relevant to this. The point is, MRPT and Annoy are both C++. MRPT was developed as part of somebody's postdoc at a university, and they did months of work. And their code, the total code, the lines of code that I wrote, it was about 500, maybe 600. And MRPT, I did essentially the exact algorithm that they did because I liked their algorithm. This was, I think, around 2,000 lines of code in C++. And they did a lot of work to optimize it. And so the point is, I was somehow able to write like a faster algorithm than they were with just a couple months of work. And, you know, I was doing other stuff too. Like this wasn't the only thing I was working on. And so this is just an example of Julia being that you could that it's easier to iterate and write the code, and then in the end you can have a very fast result. And so I'll show you one other detail of writing in Julia, which is, so we're going to go down. These are all my functions. I added this macro here. This is an at inbounds, and this tells, I don't know exactly how it works, but it tells the compiler not to do a bounds check on this loop. And that will actually happen down in the compiled LLVM code. And so inlining, I don't know what this is, but I know that it's some kind of compiler optimization, and it made my code faster. But the point is, like, here's Julia, you know, they have this macro that wraps your code, and macros, they take in code as arguments. And then when the code is compiled, they'll like write code inside of the code that you pass them. And I want to show you another thing. So this is a threads X package. And this is the map function. And if anybody doesn't do functional programming, map takes a first argument that's a function, and it calls that function on every argument in an iterable over here. So it's gonna call my function. And threads X, what it does is it just multi-threads map for me. And this is possible because of like it's simple tools from Julia's dispatch. So they just went and wrote a way to make map multi-threading. And so I don't know much about multi-threading. I didn't have to do anything to like call threads at all. And so if you look, here's my example. I'm going to allocate 4 threads. So I run some Shrike code. Here's my command. Using Shrike, I make a Shrike index, and then I time creating a k-nearest neighbors graph of this Shrike index. And if you look, it took 12 seconds. Here's all the allocations, right? And so now I'm going to run this again with 4 threads, and it took 6 seconds. And basically all I did was go and use that threads X package to replace map, all the places where I had map in my code. And this is just one of the ways that like Julia has all kinds of things like this where because of dispatch and because metaprogramming is so natural, people write these amazing like optimizer packages that you can just drop in and they work. And that's one of the things I like about it. So let's see, how much time do I have? Am I finished? Did I just have 30 minutes? Okay, I'll keep going for a little bit. Okay, well, I have a few more things that I can talk about here. Let me just see what other windows I had open. Okay. So what I want to go into next, maybe we can look at another. I'm trying to decide if we should look at another package that I made or not. We're going to go to just a little demo. So this is an example of one of the things that Julia can do with multiple dispatch. I'm using a package. Let's see. I'm using a package called zygote. So you just do add zygote like this. Oops. I'm using zygote. Add will install it. Okay, so zygote is a package for differentiable programming. And what they did with zygote, once again, I don't understand all the details, but but basically they took every function, every basic operation that you can do in Julia, like a plus, a minus, like the mathematical differentiable operations, the max function, the min function, and they wrote a method for its gradient, for taking the gradient of that function. And there's some magic that happens here. So basically, if you can think any function that you can think of, so I'm going to write f of x. Here's my function. It equals, we're going to do x squared plus 6. And let's do minus sine of x. All right, so hopefully that will work. Let's call f of 1 to make sure. All right, so it looks like it runs at least. And so zygote introduced a function called gradient into the namespace. And so notice I just wrote f. It's just a function that I made. And I'm going to say take the gradient of f at the point 1. And it spits out the gradient. So this is actually going to be like the derivative with respect to x at the point 1. And so, you know, if anybody does machine learning, let's make a machine learning layer. So let's write our sigmoid function. That equals 1 over 1. Is it plus? Yeah, I think 1 plus e to the negative x. I think that's sigmoid. Let's see if I'm right. Oh, that's right. Let's try it now. Okay, we're just going to assume that that's sigmoid. Let's see, it should be 0.5 at 0, if I remember right. Okay, so we're good. And what we're going to do is we're going to make a variable w. It's going to be our weight vector. This is going to be a random. It's going to be a, we need a one-dimensional output to take the derivative of it. So we're going to do a, let's see, we want to do matrix multiply. We want 1 row, and we're going to do 10 columns. So there's our w. And we're going to do a bias, b. That's just going to be a float. It's going to be 2. And then we're going to make our neural network layer. We're just going to call it L of x. It's going to be sigmoid of w times x plus b. Everyone's pretty familiar with that. And so now what I'm going to do is I'm going to call gradient of L. We're just going to plug in a random length 10 vector. I think it's going to be a column vector automatically. If not, we'll just change the dimensions. So gradient, oh, sorry, we're going to do gradient of L at a random 10-dimensional column vector. All right, let's see what happened. Okay, I understand. We have to put in a, this tells dot plus is when you do element-wise addition. Let's try it again. All right, x, so we're calling exp again. So we're gonna redefine sigmoid. I need to do an element-wise exp. This is what you get when you get a live demo. Real programming, this is what everybody does every day. Okay, what is this saying? Once again, okay, we got to do our dot plus and dot divide. So I'm going to go into sigmoid and tell it to do element-wise everything. Give me a second. It will work. All right. So we need to do element-wise divide, element-wise plus, because it's getting an array argument now. And so we're going to try again. All right, output is an array, so gradient is not defined. Perhaps you want a Jacobian. We'll just do Jacobian of L and rand 10. All right, so that is, I think that there might be, you can see there's some details right there. Was a problem, output is an array, so gradient is not defined. Gradient should be defined And I thought that I did it so that we would get a one-dimensional output. I tried to do that on purpose because I knew you needed a one-dimensional output to call gradient. But instead I called the Jacobian, which is just, the higher dimensional gradient. But the point is, maybe let's look at what happens when we call L, just so that we can, for completeness. All right, we're getting a one element vector. So maybe what we should do is wrap it all, or we could do it at 0. We'll get the L of X, and maybe we can try one based indexing, everyone. That's right. All right, let's try running L again. All right, so now it's giving us a float. Let's see if we can call gradient L at rand 10. All right, now we got a gradient. So that is your the gradient with respect to your vector X at that point, that random point. And so this is cool because I'm going to go a little bit further with this, and then we'll be done. So I'm going to do something weird, right? F of X, something that might not be differentiable. And I honestly don't know if max will work. Well, we can give it a try, but let me start with something simpler. Rand. So I'm just going to generate a random float times X. And we're going to do gradient of F at the point 1. And it gives me a gradient, even though the rand function was in there, right? So, and it's like, okay, that's kind of interesting, right? So why don't we try something even weirder, right? Like, let's take max. Oh, I add this maximum rand. Let's do 10 random numbers times X. Let's take the gradient of that. All right, and it was random is uniform from 0 to 1. So our gradient is just going to be whatever scalar. And it was able to somehow go through the, now you might be saying, okay, well, this is just going to generate a scalar, right? So, and then just give you whatever derivative that is. So maybe we can mix it up a little bit, and we can put X inside of here. We're going to dot elementwise multiply, and then take the maximum after we've multiplied by X, right? So that should be a little trickier, right? Let's see what happens. Oh, well, it works again, right? So this is like Julia, what they've gone through all of the operations like max and rand and like all those things, and told the underlying structure how to track derivatives back through it. It's very elegant. You can read the documentation. They have a paper about how they actually did it. But it's very cool. So, in Python, you're using things like JAX, and you have TensorFlow and like tape, like TensorFlow uses like, I think like a graph, that like keeps track of every different operation, and you go back through the graph, and this doesn't do that at all. It can literally call through the function and then afterward call every single operation backward after they've been called. And it, once again, you can hear that I don't really know what I'm talking about. But I read about it and I was very impressed. And that was like, 3 years ago. But anyway, I think that's about all I have. And if anybody wants to ask me some questions, they're welcome to. Okay, I heard, will there be a Julia deep learning? That's what I got. Yeah. Yeah. So Julia for deep learning uses Zygote, that package that I just showed you. And let's see. So my opinion about Julia and deep learning is that Julia is about as easy to use as PyTorch. So like when you're writing code. So let's go and look at Flux is the Julia package for, it's the ML library that doesn't make you tensor. And we'll look at the document. Actually, we're looking at an example so that you can kind of compare. Let's see, maybe if it will take us to the model zoo. So here's their examples. And let's look. All right, so vision. Vision's probably, who knows what you're familiar with. So let's look at CFAR10, VGG models. Let's take a look. So VGG CFAR10. So here they process their data, get the train. And so here's the model. And you define a whole bunch of layers. So you can see how this looks a lot like kind of PyTorch, how PyTorch works, right? And here's all of our nice layers, and we put them all in a chain, and every one of these zygote can differentiate back through. And then they call train, they make this train function. So once again, loss, it's just a function, your loss function. It's not like, it doesn't come from some package. You can just write whatever you want for your loss function, which has been cool for me because I've done a little bit of research into neural ordinary differential equations. And so like, I was actually backpropagating through a numerical differentiation solver. A numerical ODE solver. And so that's where Flux takes the gradient. And yeah, so here's their epoch loop, right? So they send the data to the GPU, and there's your GPU function. And then you take the gradient and then you update. So these are your parameters, and this is the gradients. This is the optimizer that you're going to use, and the optimizer here is Atom. So it looks pretty much, to me, it looks pretty much the same as PyTorch. And the thing though, where Julia has an edge, there's one place where Julia has an edge, is that Julia can write GPU kernels for you. So rather than, with TensorFlow, if you're going to be on a GPU, you're going to go in and you want to do this architecture that nobody's ever done before, and you have to write your own custom GPU kernel, and it's just the worst. Julia has some packages. Let's look at Julia CUDA. So CUDA programming in Julia. This is for working with Nvidia drivers, I think. And I don't know if they have any details in their README, but I'm pretty sure that this package, the goal of it is to be able to take your code and write a custom kernel just for you. And that's something that Python can't do right now, as far as I know. So I learned about this a year ago, so things might have changed because things change fast in machine learning. But that is one place that Julia shines in deep learning. So you can see how the process is, if you dig in, and I wish I knew more about, I understood more about it so I could tell you, but it's a lot more natural than the Python tools for taking derivatives, and you have these meta programming tools that can write code for you to generate your GPU kernels and things like that. So Julia has potential to really be amazing in deep learning, but it's not there yet. And along with that, it doesn't have tutorials. So anything that you want to make in Python, that's any ML thing you want to make, you can Google search it and find, like, just copy paste code to make it in almost every case, unless you're making something really crazy. But in Julia, that's not true. Like, it's hard. You have to know a lot of exactly what you're doing, and it makes it a lot harder. Like, the tutorials don't exist like they do for Python. So long answer, but that was a good question, and I feel like I didn't really address it. And so yeah, that's my answer there. Oh. So Julia has a great open source community, which is on, let's see, it's something, the Julia discourse. All right, I'll just show you that a little bit. So this doesn't answer your question exactly, but I like the Julia discourse. You can ask questions here, and people love to jump in and answer. Like there's a ton of support from people here, and it's much better than Stack Overflow for Julia. Another thing is you just do learn Julia, and they have this is actually a company that they started, and they have a manual, some exercises, and they hired some educational people, and they have these different courses and all the different things you might want to do in Julia, and they're great. And there's my article, one of the top things on Google. All right. So I basically just use Python and Julia. I know a little bit of C++. I learned it maybe 5 years ago, but I haven't really used it. And finding the right tool, I don't really know. I guess I just use Google. And I try and find something that works. And a lot of times I just write stuff myself. So a bit about the kind of research I do. I've primarily been a like network, complex networks researcher. And so I use like network analysis tools. And I'm also interested in like dynamical systems, like how things that are interacting via a network, how they affect each other and how they evolve over time, and specifically in brain computation. And so I've worked on a like a model of neurons firing onto each other and like that kind of thing. And so the tools that I use are like, there's like a Python package for modeling neurons. There's, network X in Python that I've used. And then Julia has some network packages, and they have like numerical ODE solvers and that kind of stuff. And I also, when I do deep learning, I use Julia. But yeah. Can you repeat it? I heard something. Yeah, thank you for this question. I didn't address this. So I'm going to answer you in some detail. We're going to look back at the package that I made. So with Julia, you don't have to specify types. Just like in Python, you don't ever say what the type of any variable is going to be. And in Julia, you don't have to, but the way to write fast Julia is to add type annotations to your code. And so the reason that this code in the package that I wrote is fast is because if you notice, every variable, I annotate the type. And there's some weirdness about this. If you look, I have a strike index type that I made, and it has this T in brackets. And this T is a parameterized type. It can be anything. And strike index is going to be like a strike index of floats, 64s, or a strike index of float 32s, right? And this abstract array that X is going to be, it can be basically any subtype of abstract array with the type T, and it just has to match this type. So the point is, there's a little bit of details beyond Python, right? And you have to make sure that your function is type stable, so that if you specify the types exactly in the arguments, that the compiler can determine the output of this, of the return value. And if you have type stable code, the compiler takes away all of the difficulty and all of that stuff you're talking about that makes C++ really hard. And then if you don't have type stable code, then your Julia is just going to be really slow. But that's the work you have to do in order to get fast Julia. You just have to give type annotations to everything, and you can do as little as just index with do a type annotation with the parameterized type. So I could make my function. So here I'll show you parameterized types real quick. I do f of x. Oh, sorry. F of x down here at the bottom is type t, and where t, that's what you have, this is the notation, and we're going to say equals x squared. And so what this says is this is generic function. F is now, it's now, I've annotated the type, but it can be any type. And what the compiler will do is it will generate versions of F for every different possible type that it could receive. And so this is still a very abstract, generic way of writing that's useful. And so as long as, the short answer is, as long as you've given type annotations to everything, then Julia is very fast. And you can write pretty much code that looks like Python. Oh, yeah. Yeah. Sure, I'm happy to share contact. Okay, yeah. Yeah, that's great. Yeah. Yeah. Hmm. That's a topic I haven't really thought about before. Um, let's see. No, I like the question. I want to think about it a little bit because yeah, I agree with you. Matlab is very fast. Like for some of the things that you can do with Matlab, it's like, my goodness. In fact, Julia spent a lot of time trying to beat Matlab's, I think their sort function, or it was one of those like low level functions, and Matlab was very fast, very good. And so when I think about Matlab and Julia, I think about Matlab is not a general purpose language, right? Like it's specific to engineering and like mathematics, and so it's almost like better for students because it's just tailored to just do math, right? So with Julia, there's the additional overhead of, because it can do more things, you have to learn to be able to use it. And that might not be true exactly, but and then when I think about like why these languages are good for machine learning, with both of them, you have a natural expressive way of talking about math. So maybe that's another piece beyond the speed. Julia was designed to be really expressive about mathematics, and so was Matlab. And they even said they were trying to be like Matlab, where it's just so natural to write math code. And so, under machine learning, there's just, a bunch of math and languages that are expressive and able to talk about that stuff and also be fast seem like great choices for ML. Thanks. Bye.